Okay, good. So welcome. Today we're going to do symmetry breaking, which is a very interesting topic. It's a very simple thing we're going to do that gives very weird consequences. And moreover, we're going to explore the Higgs mechanism. So we're going to sort of motivate this idea of the necessity of a Higgs boson and a Higgs field. Right. So this is going to be what we're going to do today. Good. So the homework, so here's my plan. So tomorrow we're going to do our normal session, and I'm going to do gravitational waves tomorrow. And yeah, so I have all of that planned. If Jenna needs it recorded, I'll record it. I'll find out. And my plan for next week is to do a lecture, to start doing a lecture on more modern topics in theoretical physics, and to take you guys into the modern, sort of the more, the things we need to know to do some nice problems. So next week, I'm going to give a lecture on spinor helicity for all of you, and we will talk about the basics of spinor helicity. And next week, I'll also do an introduction to conformal field theory. So this way we can kind of get up to speed with the modern aspects of theoretical physics. So those of you that I said read the spinor helicity, it's okay. I'm just going to teach you it because it's so important and I want you to learn it. So to that effect, the homework then for this week is going to be some reading on Yang-Mills theory. Because I want you guys, I'm going to teach you Yang-Mills theory proper, but I want you guys to have some background before we do spinor helicity, just the basic idea. So there's many sources for Yang-Mills theory, but sort of the best ones. So Schwartz has a good section on Yang-Mills theory. That's chapter 25 and 26. Z covers it in his section VII.1. Lancaster, Blundell cover it in 46. And Srednicki covers it in chapter 69. So I would look at all of those on Yang-Mills theory. I would obviously start with Lancaster and then go to the other books and read about it, because you should have some familiar with Yang-Mills theory, or as it's called, non-abelian gauge theory. That's sort of the other way to frame it. Because when we do this modern stuff, a lot of the stuff is done in the context of Yang-Mills theory. So this would be good for you to see. I mean, it's not a huge, it's just an extension of all of the things we're doing. See, once you learn QED, everything else is just a basic extension of QED. So it's a very, now everything should be straightforward relatively. Okay, very good. Does anyone have questions from last week about anything before we get started with symmetry breaking? Okay, good. So let me just think if there's any more logistics I need to remember. Okay, good. So yeah, so next week we're going to start the modern physics. We're going to get to the real stuff. Like I said, tomorrow I'm going to do gravitational waves. And this week I'm actually going to be in California I have to take care of some personal stuff. So I'm going to be, I have an iPad with a pencil, which I can draw on. So, that's how I drew the slides for that lecture I showed you guys. So I have my iPad. So next week I'm going to lecture off my iPad. Okay. So I'm not going to be on the chalkboard. So I'm going to do things the modern way for once. Okay. But after that, I'll be back on the blackboard. But what I was going to say to you guys is that the timing is bad, and I'm not as bold as Jenna to wake up at 6:30 for a lecture. So we're going to have to move the lecture a little bit. Jenna's going to get a kick out of that because now I'm in her time zone. So next Saturday's lecture is going to be at 12:30 Eastern. 12:30 Eastern, okay? Because then it's 9:30 Pacific for me. And this way, Jenna, the karma comes back. So now Jenna gets her 3 hours extra of sleep. So there you go. There's that. And next week next Sunday morning, I'm going to give you a lecture on our research or my research. And so this way you can get accustomed to sort of the nitty gritty of the problem I'm working on, or the types of problems I'm working on. Sound good? Okay, excellent. So we are we're making a lot of progress starting next week and tomorrow. Okay, and next week's GR topic is going to be cosmology. I'm just saying all of this just so it's on record, so I have everything straight. So tomorrow, gravitational waves, next week, cosmology. Okay, very good. Yes.
I'll just a quick thing regarding tomorrow's lecture on GR. I will be like in the way to Boston. So could you please record the lecture so that I can watch it?
Sure. So yeah, so good. So maybe Jenna wouldn't be able to make it too because she's sick. So I'll record it for you guys. That's fine. So yeah, Aryan should be here, and he'll be the one who keeps me in check when I make all my indice errors. So okay, very good. Okay, so what is symmetry breaking? Let's cut to the chase. So we have an inherent symmetry. Okay, so first of all, symmetry is very important in physics. I don't think I have to say that to this group. But there are inherent symmetries in the fundamental objects we've been constructing, right? We have a Lagrangian that is the fundamental object of our field theory. And now I'm going to tell you that I'm going to somehow break the symmetry. What do I mean by this? So let's just start with sort of the basic object we work with in this kind of context. So what is the basic object we're sort of trying to compute in quantum field theory? Well, it's something like this. A standard correlation function, right? Where omega is the vacuum state for the interaction, right? This is like also Johnson's not having that was another thing, right? Johnson's not having a session today. So, I don't know if you want to stay on or if you're meeting some other time to work on some of the GR problems, you let me know. Okay, so anyways, let's get back. So this is the basic object we want to compute, right? In quantum field theory. Is this okay? Right, and this is just your standard vacuum expectation value. Now, what we're going to find is when we break the symmetry, quote unquote, of the Lagrangian, which I'm going to show you what that means, the vacuum does not stay empty, okay, in the interacting theory. That is so I'm just giving you the punchline right away before we even get started, that the vacuum is not really empty. And the reason it's not empty is because of symmetry breaking. However, what we're going to have to figure out is physically, what does it mean when the symmetry breaks, right? Does it mean that we get new particles, right? Does it mean that we get some weird excitations of the fields? Like, what does that mean? And that's the question we're going to answer. But first, let's go through mathematically. What do I mean by breaking the symmetry? And then we'll analyze the consequence of that. Is everyone okay with that? So let's start with sort of a generic Lagrangian, where you have some kinetic term, so 1/2 d mu phi squared minus some potential, minus u of phi. Right, this is our standard Lagrangian. And in phi to the fourth theory, u of phi is our standard mu squared over 2. So instead of m, I'm using mu for the mass, which is going to be clear why I'm doing that. Phi squared plus lambda over 4 factorial phi to the fourth. This is just our standard potential energy term in phi cube theory. And of course, this Lagrangian has a global symmetry that if I let 5x go to minus 5x, the Lagrangian stays invariant. Right? That's just a global, almost like a translational symmetry of the theory. Okay. So let's just say, let's like draw out how this potential is going to look, right? Because we can do that presumably. So if I put phi on the x-axis and I put u of phi on the y-axis, I get a potential that looks like this. This from this basic thing. And if mu squared is greater than 0, well, then I have a minimum. The minimum of this potential is at phi equals 0. So min phi equals 0. And since I have a symmetry that phi goes to minus phi, this is always, sorry, this should be centered at the origin. I'm not very symmetric with my grid, it's a little off center. But you get the idea. I have a minimum of the potential at phi equals 0. Right, and so this corresponds to the vacuum. So this is basically like me saying that omega phi of x, so this vacuum expectation value equals 0, right? Because now I compute, I have some potential, and the particle is just kind of sitting there. It's not doing, there's nothing there, right? The expectation value gives me 0 at the minimum. That's what I mean physically by that. Okay, and what are the excitations of this phi to the 4th field? Well, we call them phions, right? That's some scalar particle we've been calling some made up scalar particle, right? And again, I just to be explicit, the mass of those phions is mu. Okay, is everything okay with it? This is our standard story, right? This is like physics 101, right? Kind of like just what we've been working with and nothing fancy. Of course, you can add all kinds of interaction terms here and derive rules and give a different S matrix. But at the end of the day, you're calculating correlation functions. Okay, that's the basic idea. Okay, so let's play a little game now. Okay, so now let's do something that seems trivial, but it's going to be very very non-trivial. So let's impose the condition that mu squared is less than 0. Okay, so this is just a very, so what does this do to the Lagrangian? Well, it changes the sign of the potential term. That's the basic thing that it does. Mu squared over 2 phi squared lambda over 4 factorial phi to the 4th. Okay, it changes the sign of potential term. This is a big deal. Why is this a big deal now? Okay, and this is not at all obvious from just staring at this, but by changing the sign of the mass term, I actually now, instead of having one minima at phi equals 0, I have 2 minima. Okay, and I'm going to calculate the other minima, but I have a minima now at phi naught equals plus or minus, let me just make sure I get this right, 6 mu squared over lambda to the 1/2. I'll show you how I get that. Okay, and I get a potential that now looks like this. So here's u of phi, here's phi. Now I get a potential, if you plot this, that looks like this. Okay, kind of crazy. And now I have 2 minima. Okay, how do I calculate the minima? So for anything, saying that I want to find a minimum means that I have this condition, du d phi equals 0, right? That's what I mean by a minima, right? Just from calculus. And if you compute this, you will find that now you have 2 minima, one at 0 and one at plus or minus this 6 mu squared over lambda to the 1/2. Okay, so simply by changing the sign of the mass term, I get 2 minima. Okay, can someone intuitively tell me now what's the problem with this now? This is like a big problem. So before, right, I had 1 minima, right? And no problem, right? I said that the vacuum was the vacuum, right? The vacuum was empty, right? When I calculated that correlation function. Are we okay with that? So now if I ask you, Olha, which vacuum is the right vacuum state here? Can you tell me?
To our right,
This one?
like all of them. Why
They're
not?
both right, exactly. Okay, so that's the good. So that's the intrinsic part. We have two vacuum choices now. One is this and one is this. This is like weird. So now we have a choice of two vacuum. So that's the immediate mathematical consequence from this, right? Very good. So let's say we don't take this vacuum. Well, now we've broken the symmetry. Now phi naught going to minus phi naught is not a symmetry of the Lagrangian. If we take this vacuum, the 6 mu squared over lambda to the 1/2. Okay, and now we have new physics. Okay, so this seems kind of insane. You change the sign and you get some new physics. And the fact that the physics that we get, which is really amazing, which you're going to see in about 20 minutes, let's just do some more exercise, is going to correspond to something we see in nature is pretty amazing. So this is what I mean by symmetry breaking of the Lagrangian. It's imposing a new vacuum and or obtaining a new vacuum. And this is sometimes called spontaneously broken symmetry because you have the choice of two vacuum states. Okay, so now what I'm basically saying in familiar language is that this correlation function is not equal to 0. Okay, that is what we have obtained. Also, there's many sources on spontaneous symmetry breaking in the other textbooks, which you should, if after this. I didn't assign the chapters because I want you to read about Yang-Mills, but you should certainly read about this. Okay, now your natural question is going to be, well, what does this even mean physically? That is obviously the natural question, right? And that's where we're going to get something very interesting, extremely interesting, actually. But let us first do some more math and build up one more technique that we're going to need to use, okay? So the question you should be asking, though, you should be asking yourself, what are the particles that we get from this broken symmetry? That's what you should be asking, right? Because now, obviously, we have stuff. We have stuff from the fact that we've broken the symmetry in the Lagrangian. Now the question is, what is that, and how does that manifest itself in the real world? That's a more difficult question, right? So we're going to answer that. But first, a very important technique we use in this sort of approach is to take this minima, to take this potential and this minima and Taylor expand around it. So this is a very good technique in calculus. If you take the minimum of a function and Taylor expand around it, oftentimes you can get a lot of interesting stuff. So let me show you how to do that. So let's say I choose some minima. So I have some u of phi minus phi naught. Okay, and I want to Taylor expand around it. Can you guys write the Taylor series for this? Or should I? I'll do it. So obviously the first term is just going to be u of phi naught, right? Plus du d phi evaluated at phi naught, a phi minus phi naught, right? So it's the first derivative of that guy. Plus 1 over 2 factorial d2u d phi squared evaluated at phi naught, phi minus phi naught squared, plus blah, blah, blah. Right? That looks like a Taylor series. Are we okay with this? Okay, so I'm just expanding around the minimum. Okay, and I can write this now just in sort of our language as u of phi naught plus mu squared phi minus phi naught squared plus dot, 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 right? Where u of phi naught is some constant, right? Because that's just the minimum. So it's either 6 mu squared over lambda to the 1/2 or 0. But obviously 0, we can say that 0 is the trivial minimum. it's trivial, right? Because that's just exactly, I get all the physics I would expect. Okay, very good. Okay, so now I'm going to write down a new Lagrangian with this language. So now my symmetry broken Lagrangian, or sort of the Lagrangian with the new vacuum, is very simple. It's just 1/2 d phi prime squared. I'll tell you what phi prime is in a second. Minus mu squared phi prime squared plus higher order terms, which we ignore, right? Because from the Taylor series, you're going to get a lot of higher order terms. Okay, and I've simply defined phi prime as phi minus phi naught. Okay, so this is my new Lagrangian, which is, which is okay. And I can obviously take these terms and expand them in this way. Is this okay? Okay, very good. Okay, now this seems a little bit abstract, right? This is like, now we're going to make it concrete, and I'm going to show you some examples, and you'll get some consequences from doing this procedure. Okay. Yeah, so another way to say this is that this Lagrangian, right, violates the symmetry of the Hamiltonian, right? That's another way people say it, because I was just thinking about that, because it's violating that basic, this is a basic symmetry of the Hamiltonian, which is now violated. Okay. Now the mass of the new phions, now mu equals the square root of 2m. Right now some new excitations have a new mass. That's another consequence. But let's explore this now. Like, what's going on here? We know we're getting a new, is everyone clear on that? We know we're getting some new particle. That's sort of intrinsic to this procedure. Okay. Okay, let's cut to the chase now. Now we have all the math we need, which you'll see more clearly how I use this Taylor series expansion. But again, now the main point is that this correlation function, omega phi hat of x, omega does not equal 0. Also, remember, usually I put zeros for the vacuum, right? But remember, when I put omega, I'm talking about an interacting correlation function. That's the only reason you put omega instead of 0. Okay, and what is phi naught? Phi naught is very simply 6 mu squared over 2 over lambda to the 1/2. If you guys are confused on how to find minima, go to any calculus textbook and see if you can compute that. It's very simple. You just set that derivative to 0. Okay, and now I want to write down a new Lagrangian of two types of scalar particles. Again, that's what I want to use as my example. So let's write that Lagrangian down. So I have a Lagrangian that goes 1/2 d mu phi 1 squared plus d mu phi 2 squared. Okay, so now I just have two sets of scalar particles. Plus mu over 2 squared, phi 1 plus phi 2 squared. Minus lambda over 4 factorial, phi 1 plus phi 2 squared. Is this all okay? I just have two sets of scalar particles now, phi 1 and phi 2. Now I want to see how the potential works with this. So the first thing I'll say is that this Lagrangian has a global SO2 symmetry. So this has a global SO2 symmetry. This is, have I broken the symmetry yet in this? Not yet. I will in a second because I'm going to choose this vacuum. But this Lagrangian on its own has a global SO2 symmetry, right? If I rotate the fields, I get the, it leaves it invariant. If I boost things, leaves it invariant, right? All of the same symmetries we know and love, and it enjoys those symmetries. Now this potential, the potential this guy makes is what we call a Mexican hat potential. Okay, why do I call it a Mexican hat? Well, I don't call it this is what everyone calls it. So it's funny because you're reading a paper and you see Mexican hat potential. It's kind of funny. But here's the way to think about it, okay? So let's say you take a wine bottle, okay? You take a wine bottle and now you, how do I describe this? You push the back of the bottom of the bottle and it makes a bump in the bottle, right? So now you have like the bottom of the bottle, but you have a little hump in the bottle in the center, right? Because you push the bottom. So that looks like a sombrero, right? Like a Mexican hat, right? So now think about what the particle can do. That's the potential. So now either the particle can go around like this, right? Right? Or it can go up the hump and down the hump, right? It can get a little kick up and down. So it only has two options in this potential. It can either go like this, or it can go up the hump and down. That's the only two options in this. So this is the Mexican hat potential. This is a very good Lagrangian to work with to describe what I'm going to tell you about. So that's the sort of physical picture. And so this has an infinite number of minima, right? Because I can just take different values of lambda and mu, and I can get different just values of the minima, right? So here, phi1 squared plus phi2 squared equals 6 mu squared over lambda to the 1/2. Oh no to the 1/2. Just this because I squared it. Sorry. And of course, now I take my symmetry. So now I'm going to break the symmetry. So now my potential is minus mu squared over 2 phi1 plus phi2 squared plus lambda over 4 factorial phi1 plus phi2 squared. Good. So now I'm just breaking the symmetry. That just means it seems kind of unique, but it just amounts to changing a sign. Okay, good. Can I erase? Okay. And let's do some more with this. So this is what we're going to work on for a few minutes. So here, let's say x equals phi1 squared plus phi2 squared. And of course, I'm demanding that du d phi equals 0. So I'm working with all the minimum points. And so I get, if you work it out, I get that the minima all lie on a circle, which you can kind of see from this whole construction. So if I have phi1 here and phi2 here, and I'm plotting those points, I'm going to get all the minima on a circle and an infinite number of minima. Okay. A lot of this is just kind of like some basic fun calculus stuff. And again, I have phi1, phi2, and I choose one vacuum. So I have the choice of two vacuums or 0, except now the 1/2 is gone because I have phi1 squared plus phi2 squared. Oh no, actually, wait. No, in this case, yeah, square root stays. Sorry, it's the same minima. The minima doesn't change. And now I'm going to write out the Taylor series expansion around the ground state, okay? Or around this minima. Shall I do it? Okay, and hopefully this will be a little bit more concrete because it's still kind of abstract. Okay. And I got to tell you, the first time I read about the Mexican hat potential, it was very funny. I don't know why we call it that. But so let's say that phi1 prime is now phi1 minus my minimum. Okay. And phi 2 prime is equal to phi 2. Okay. So I can write a new potential after Taylor expanding, right? That goes 1/2 d phi prime squared for 1 plus d phi prime 2 squared plus, minus, because this is a new sign, minus mu squared phi prime 1 squared plus order 5 cubed and higher order terms. 5 prime. Cool? So obviously I didn't write out all the Taylor series terms, but I know what I get at the end of the day. And this is what I get, my new Lagrangian. My symmetry broken Lagrangian, right? Okay, so now we can make some very interesting comments, okay? So first of all, let's draw the potential or the minimas. So I have phi 2, I have phi 1, and I have all the points on the circle. So now there are only 2 options my particle can have, right? In terms of where it can go, right? It can either go out this way along phi 1, right? And that would mean that it stays at 0, right? Because this is phi 1 minus the vacuum I picked. So this is just 0. Are we okay with that? This is the first minima. And then this guy is the 6 mu squared over lambda. Yeah. So now if I take that minima, well, then I'm going up the hump, so to speak. Right? So the phi 2 minute, so now I've put both in. That's why this is a good Lagrangian. I have 2 options. The phi 1 minima is just 0. I'm just kind of moving in the gutter, right? The literal gutter. And the phi 2 guy said, okay, I'm going to go up and down this potential. Okay, so now the very crucial observation is that, first of all, the phi 2 guy is going to be the x. So the phi 1 field gives us the standard excitations, right, of particles that we're used to. The phi 2 field is going to give us the crazy particles. But can someone tell me something? So let's, okay, so are we okay with that when I say the phi 2 field is going to give us the interesting physical particles? Because I'm just imposing that new minima on that, okay? 6 mu squared over lambda. This guy's 0. But okay, let's just say you're a little unclear about that. Look at this Lagrangian, okay? Do you notice something funny about it? So, okay, this term seems okay, right? The kinetic term seems fine. Let's look at this term. And this comes from taking derivatives. So if you work out this Taylor series, you'll get this Lagrangian. But I have a mass term for phi 1, right? Do I have a mass term for phi 2? No. Okay, this is strange. So this comes from taking derivatives. So when you compute this, you'll find that the mass term for phi 2 vanishes. So somehow the excitations from phi 2 are massless particles. Okay, that's the first kind of strange thing. Okay, because there's no mass term in the Lagrangian. And so this is a manifestation of what we call Goldstone's theorem. So this is a very, very important idea that comes from symmetry breaking. You'll see this all the time. And the rule, here's the rule. And you never forget this now because it's going to come up even when you do research. You're always going to think about Goldstone's theorem. And the rule is that breaking a continuous symmetry, if you break any, we've broken a continuous symmetry here. We've broken the SO2 symmetry. that it used to enjoy, that phi 0 goes to minus phi 0, breaking the inherent symmetry creates Goldstone modes. Goldstone modes being these particles. And these particles are called Nambu Goldstone bosons because they're scalar. Okay, so anytime you break a continuous symmetry that is, and it's non-trivial, you're going to get Nambu Goldstone bosons. That's kind of weird. However, now you should ask me this question. Kyle, are these particles real? Right? Like, do we find Nambu Goldstone bosons in nature? They're usually just called Goldstone bosons, but I say Nambu because he also discovered it as well. Usually we just say Goldstone bosons. What do you guys think? Do you want them to be real? Do you want nature to have Goldstone bosons in it? They're not real. They're not physical. Okay? There is no massless scalar particle in nature. But you're going to go, well, wait a second. There's no massless scalar particle in nature that just lives in the vacuum or lives without any interaction. Okay, this is kind of funny. So now you're like, wait a second, what? Then how do we deal with this? Right? That should be the natural question. And this is where we're going to get to the most, honestly, this idea, so there's a lot of amazing things in QFT. That's why I love it so much. But this, what I'm about to show you is one of my favorite. It's called the Higgs mechanism. Handles this. And actually, Higgs won the Nobel Prize for this, along with collaborators for the Higgs mechanism. Okay, so let's see. So now we have tension. Somehow, okay, I created some new physical degree of freedom, but it's not physical because experimenters didn't find it. But we need to reconcile that there's an inherent symmetry breaking. Remember, I say quantum field theory is very constraining, right? It's a very constraining theory, which is good. The more constraining your theory, the better, right? Because then it's more precise. But we have an inherent symmetry breaking. We must reconcile this in the theory. And I'll show you how. And we're going to have to rely on gauge theory to really reconcile it. Okay, any questions before I continue? Okay, so sorry, I know you guys were rooting for the Goldstone bosons, but actually, you know, they're a very good test of whether symmetry is trivial, right? Let's say you enact a symmetry of the S matrix or something, and you get these Goldstone modes from that broken symmetry. You know it's a non-trivial transformation because you're getting something new. So that there is something to it mathematically. Which, by the way, a lot of times people call these soft particles, right, that are created. A lot of times, in some cases, they're just Goldstone bosons that are created from these symmetries that people act. Okay, so they're massless. Okay, so let us resolve this problem, shall we? And let's come to some big physical conclusion. That's what we want to do. Because this is like very unsettling, that I do something that a Calc 1 student could do, change the minimums of my potential, and everything gets crazy. So let's figure that out. So let's start with a nice complex scalar field theory. So let's write down, obviously, to write down the Lagrangian. That's the natural step. So d mu psi dagger for the complex field, d mu psi, right? That's the complex field. That's the standard field. Plus mu squared psi dagger psi. Minus lambda psi dagger psi squared. Good, this is like a complex Lagrangian. I've taken out my phi field, so it's not like Yukawa theory, it's just. So this has a beautiful U1 symmetry. So this enjoys a nice U1 global gauge symmetry. So can someone tell me what that means? Like, what is the transformation that maintains U1 gauge invariance? What's the transformation that this Lagrangian enjoys? What can I let psi go to for it to have global gauge invariance?
Like moving, just
Yeah,
not
exactly.
rotating, but just moving.
Yeah, so good. So I can just write that out as some e to the I alpha, right? Where that's some phase, and yeah, good. And that's what I mean by global U1 symmetry. And now you guys know a little bit of the language of morphisms, although Johnson is going to really teach you a lot about this. But it turns out that U1 is isomorphic to SO2. And so we're not going to get something too different, right? Because when I say isomorphic, I mean these guys are really the same group in disguise, which we'll see when we talk about conformal field theory, that actually the reason we use conformal field theory is that the group that tells you about conformal transformations is isomorphic to, guess what? The Lorentz group. So it turns out to be a very nice correspondence, which you'll see next week. So I'm going to switch this guy. I'm going to write this guy in polar coordinates, okay? And this is just something to make the calculation look a little easier. And what do I mean by that? Well, I'm going to let psi, I'm going to change psi of x into polar coordinates, and I'm going to write it out as q of x e to the I theta of x. So I've just, now my alpha is just some theta that I'm rotating everything by. That's just some phase. And q is the the radial vector, like where it's located, the field, as it rotates around, all the vectors in the field. Is that okay? So I've just made a coordinate shift. And so I have to rewrite the Lagrangian. So now my Lagrangian is just d mu capital Q squared plus Q squared d mu theta squared plus mu squared Q squared minus lambda Q to the fourth. Also, quick question for you guys. Do you find GR easier than this or harder? Or the same? Indifferent? Okay, that's fine. That's fair. Okay. Right, so now I have two fields, right? Q of x and theta of x, right? Like two different kinds of parameters I can vary. And Q will just go to Q in this construction. So the positions will be fine, but what's going to change is theta. I'm going to change theta by phase, which I can because I have some U1 symmetry. And now I say, let's break the symmetry, shall we? This is very anticlimactic because all it means is changing the sign of the potential. So now breaking the symmetry means that U equals minus mu squared Q squared plus lambda Q to the fourth. Okay, there, we've broken the symmetry. It's not that bad, right? Just change the sign because that's going to give us new minima or a choice of minima. Okay, can I write it? Can I erase? Okay, and what is that new choice of minima? You do the calculation, you get something very similar. You get that capital Q naught is now equal to mu squared over 2 lambda square root. Okay, so very, very similar. Now, of course, I can write this as a Taylor series, right? And do the same things and analyze the potential. Right, so here's an exercise for you. You write Q prime as Q minus Q naught. You write theta prime as theta minus theta naught. And you write out the Taylor series expansion and you see what happens. Okay, that's for you guys to do. Because I want to get to the big picture. This was just another example. Okay. Can I erase? Okay, good. That's an exercise for you to try. Okay, so now, good. So now, well, how do we reconcile the Goldstone modes? And the answer, here's the answer, here's the punch. We need to gauge fix our Lagrangian. That's the punch. If we wanna, you know, just say it in one sentence. The solution to this problem, and this is miraculous. It's not like it was meant to, right? Gauge invariance seems very silly. The reason we use it is because it gives us so much insight that we didn't know was there, right? And it seems kind of like, it seems contrived. It seems like, I mean, you obviously wouldn't expect it. So the first step is to write down this Lagrangian in a gauge invariant way, right? Obviously, the Lagrangian I just showed you has a U1 symmetry. Is it completely gauge invariant? Does it have a local U1 symmetry? No, right? Like if I took psi to psi of e to the I alpha of x, it would not be invariant if I had a local, right? How do I make this locally gauge invariant? I need to gauge fix it. What do I mean by that? All my derivatives become covariant derivatives, right? And so on. So I have to get rid of all of the redundancies from this alpha of x. Are we okay with that? Read the chapter in LB on gauge invariance, if that's still unclear. Okay, very good. So let's write down the gauged complex scalar field theory, okay? And it's not anything crazy. So the Lagrangian now is equal to d mu psi dagger minus IQ a mu psi, right? Because what is my covariant derivative? Sorry, psi dagger. What is my covariant derivative equal to? So I'll just jot this down. So the gauge covariant derivative d mu is equal to d mu minus IQ a mu, right? So that's my, this is what I mean by gauge fixing, because this is going to cancel out the extra terms from that that local symmetry. So similarly now I get d mu psi plus IQ a mu psi plus mu squared psi dagger psi minus lambda psi dagger psi squared. Okay, and then we add our ENM gauge fixed term. Minus 1/4 F mu F mu. Okay, this is the Lagrangian. This is like your basic Yang-Mills Lagrangian, you'll see. Or even from ENM, right? And now I have imposed local gauge invariance, right? Psi of x can now go to psi. Well, let me write this less. Psi can now go to psi times e to the I alpha of x with this Lagrangian. Now I've imposed local symmetry. Is this okay? I've just literally replaced the derivative with a covariant derivative, and then I've added this term. You'll see why. Are we okay with that? Okay, I hope so. Okay, so what have I gotten here now? So what is this Lagrangian describing? Well, first of all, it's describing two sets of oppositely charged particles, right? Psi dagger and psi, because the signs are different in the charge. That's the first thing it's describing. And these particles have our standard energy, EP equals p squared plus m squared, square root, right? Are we okay with that? So it's describing two sets of differently charged particles. It comes from this term and this term. And the second thing this Lagrangian is describing, so there's two things it's describing, are photons, right? Because of the gauge fields, A mu, right? So now I've added photons into the story. Of course, they can have some polarization, and they have energy EP equals P. All right, so they have some polarization. I can write mode expansions, blah, 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 blah. All that annoying stuff that has a lot of algebra, right? Which, you know, we don't do. Okay, very good. Okay, now I'm going to, so this is what's going to give us our resolution, this procedure. You'll see why in 5 minutes. Okay, can I erase the board? Okay, so we have a nice little theory that we've written down. Okay. I want to write this in polar coordinates again. So psi of x will equal q of x times e to the I theta of x in polar. And here theta of x is going to equal theta naught. I've imposed that minimum. And so now let's just say we have the term d mu. So I'm just going to take one term in the Lagrangian. So let's say we have the term d mu psi plus iq a mu psi, right? This is just the second term in the Lagrangian, right? So let's just see what happens when I transform to polar coordinates. So I get d mu theta, sorry, d mu q. Why would I get a theta there? E to the I theta. I'm just rewriting that term in polar coordinates. Plus I d mu theta plus iq a mu. Oh no, I put the I outside. Sorry. No, why I would have an I again? Times q to the e to the I theta. Okay, so I'm just showing you how the term would look in polar. And so I'm going to make the following shift to make my algebra, or to make it have some less writing. So I'm going to say that a mu plus 1 over q. Let me just make sure I'm doing this right with the algebra. Yeah, plus 1 over q d mu theta. I'm just going to call that something c mu. Okay, just so I save some writing. So now I'm going to write the new Lagrangian. All I'm doing is just making this a little easier for us to analyze. Okay, so now my Lagrangian then, and you can work out the algebra to this, is going to be d mu psi dagger minus iq a mu psi dagger right? Now I just need the second term, d mu psi plus iq a mu psi. That's just the second term in the Lagrangian. And now if I rewrite this in this polar coordinate way, I get d mu q squared plus capital Q squared, little q squared for the charge, c mu c mu. Good. So I just wrote this now. So now I've taken all this and just rejiggered all of it, right? It's just, you just can work out the algebra with these substitutions. Although I think this 1 over q might need to be a q. But I might be wrong, but you check. Very good. Okay, this is gauge invariant. Let's write down F nu, the field strength tensor in this language as well. So now obviously standard, this is just d mu a mu minus d mu a mu. And now in my new sort of polar coordinate language, I can write this now as d mu c nu minus d mu c mu. Just taking these guys now. Okay. Basically, what I'm saying is all of the terms from a mu, I've sort of just packaged into this c. Okay, just to make everything shorter. So I don't have these long expressions. And so now can I write the full Lagrangian now in this language? I've just showed you term by term. Now let's just write out the full Lagrangian. Is that okay? Okay. I hope this isn't too bad. I'm just literally just subbing things in. I'm not really doing anything crazy right now. If you just follow the algebra, you'll be fine. We haven't gotten to the good stuff yet. We're like almost there. I can taste it. Okay, very good. So let's write down the new Lagrangian. So now the Lagrangian equals d mu capital Q squared, right? So now I'm just subbing in what I've been writing. Plus capital Q squared, little q squared, c squared. And here, I'll tell you what, plus mu squared q squared minus lambda q to the fourth minus 1/4 f mu nu f mu nu. And here, c squared is just c mu c mu. Okay, so now I just have a full Lagrangian. Kind of nice. That's a nice way to do things. You know, whenever you're doing your own work, like if you're doing your, I don't know, algebra 2 trig homework, just come up with all these random simplifications and come up with, I did that once on a homework to make my teacher angry. So I did these, you know, like you do your homework, you have some algebra. And at the end, I would box in like one letter. And she'd be like, what? And I'd be like, look at my subs. Suffice to say, I did not get a good grade on that homework. She thought I was being too clever. I just wanted things to look elegant. Okay, now, shall we break the symmetry? Are you sure? Are you sure? I just want to make sure you're ready for this, because actually crazy things happen now when you break this gauge fixed symmetry. So let's do it. So now again, nothing really crazy. I mean, the minima are pretty straightforward. So Q naught equals mu squared over 2 lambda. You can compute that. Right? I mean, that's just like basic thing. And then theta naught will equal theta. Okay, so these are just some minima. And what I'm going to do, so now I'm going to write out the Taylor expansion. We're going to need it. But I'm going to introduce a new field for the expansion. So I'll call it chi, and chi will just be Q minus Q naught. Okay, just so it's less writing, because you know that's going to be in the Taylor series. And let's write out the Lagrangian. So it turns out the Lagrangian, so let's say you do your Taylor series, you work out all the derivatives and so on. It's going to be long. So you get 1/2 d mu pi squared. That's straightforward, right? You expect that kind of term there. Minus mu squared pi squared. Minus square root of lambda pi. Wait a second. Yeah, square root of lambda mu I cubed. I have to go term by term slowly. minus lambda over 4 chi to the fourth. So now I'm writing more higher order terms, right? I'm not just cutting it off. Minus 1/4 f mu f mu. Now I'm going to deal with the theta terms. Well, okay, let's just stop right there for a second. Okay, we get all of this, right? This is like looks familiar from all the stuff we've been doing, right? So far, other than these chi cubed and chi to the fourth terms, the rest looks kind of similar to the Taylor series expressions I've been writing down today. But we have to remember that in this C mu, what is C mu? What is the definition of C mu? C mu equals A mu minus 1 over Q I d mu theta. Okay, so now we're going to expect to see some C mu terms in this Taylor series, right?
Wait, wasn't it A nu plus 1 over Q?
Wait, let me make sure. Yes, good. Yeah, good. Okay, absolutely. So now these terms are going to pop up now. I've taken care of the Q's and I'm kind of nice. I gave you some higher order terms. I could have just cut it off. But now let's write down, which actually, I don't even know how I did those three. Let me make sure I got the chi cubed term right, because it's 3 derivatives, right? 1, 2. Yeah, you should get a square root of lambda. I'm pretty sure, but I don't know. Okay. So what comes next? So let me think. Yes, so we're going to get another m squared over 2 c squared term. Okay, because now my c is going to have a mass term. Right? Because that's a new field. That's a new object. Plus q squared mu squared over lambda to the 1/2 chi c squared we'll do one more plus 1/2 q squared chi squared c squared plus dot dot dot. I don't have it in me to keep going. Okay, let's analyze this. So let's just say you don't know any of the math to get this. No problem, because now this is what's going to give us the gravy, right? Okay, now we have to stop and just really think about what's happening. Okay? What have we done? We rewrote our Lagrangian, but gauge fixed it. We have imposed gauge symmetry, right? And by imposing gauge symmetry, we get all of these A mu, 1 over Qi d mu terms, right? That's just what happens with gauge invariance. It has very bad effects for the Lagrangian, or very interesting effects. Why? So let me rewrite this up top and let's analyze it, okay? Very good. If you're having trouble obtaining these kinds of expressions, just go slowly in the book or look it up and it'll be clear. Don't worry. I called this capital M. Okay, so we have two things to worry about, right? We have chi, right? And chi is like our radial field, right? We can call it our radial field because it's like q minus q naught in this polar coordinate thing, right? So it's like the r part. And chi is like very basic, whatever, boring stuff. You get some particle, standard scalar particle. It's the part that imposes the minimum of 0, right? The radial part. Now we have C, and C gives us all of this theta stuff that comes from this local gauge invariance. Do you notice something funny? First of all, let's say the first thing. Our Nambu-Goldstone boson, or the massless field, disappeared. I have no Nambu-Goldstone. I have no massless C term, and now I have a massive C squared term. That's crazy. So somehow, this process of gauge fixing, adding new redundancies, it's some long technical thing which we're working out, has taken the massless field and replaced it with a massive field. Okay, this is crazy. So there was a very famous physicist, you should know this name, named Sidney Coleman. You should look him up. His lectures on quantum field theory are very famous, actually. They're on archive. And he came up with a very funny way to say this. He said it's almost as if the massless A mu of X field, so the massless gauge field, right, for the photon, it's almost as if the massless field that comes into the story, because, right, this is coming from gauge invariance, right? That's why we've introduced this A mu. It's almost as if this guy's come in and eaten the massless part and replaced it with a massive part, C mu of X. It's almost like it's eaten it, and what's come out is something massive. Okay, so this is what we call this procedure. So what have we done? We've taken the massless Goldstone modes and the Nambu-Goldstone bosons. We've done a gauge transformation. We've removed the massless stuff, and we've obtained massive particles, scalar particles. From this theory, we could have obtained massive particles that were charged or whatever. And this is called the Higgs mechanism. This process. This is what, and I'm going to talk about this for a second. This is what Higgs et al., so Peter Higgs et al., won the Nobel in, what year was it? I don't know, 2013, when it was discovered at the LHC. So, okay, so what does this mean physically? Like, okay, how do we interpret this? So there's a field called the Higgs field, which is what we're going to talk about later in the course when we do the weak interaction and that stuff. And what we're going to see more in depth, which is a manifestation of this Higgs mechanism and the weak interaction, is that the Higgs field, by virtue of gauge invariance, takes these Nambu-Goldstone bosons that are there in the theory and transforms them into physical particles that we see. So in some sense, all of the photons, electrons, quarks are coming from the Higgs field. You can get all of them from the Higgs field by imposing a gauge symmetry. That's kind of insane. And the fact that we found a Higgs boson out there is crazy. So it's like a molasses, right? That's what people call it, because I mean, they don't know all of the technical details, but what people say is it gives all the particles mass and charge, and right? Because this is giving something mass, right? This is, I'm deriving mass. The fact that I can derive mass from gauge symmetry is, I don't know. You're going to have to, I can't answer that question how that works, but it does mathematically. So you impose symmetry and you get physicality. And we're going to explore this further, obviously. Okay, I just have one more technical note to make. So the fact that the Goldstone bosons are not physical, but can be removed by gauge transformation, right? So they're somehow like, you can remove them with non-trivial transformations. We say that they are pure gauge. Right, so we say that the Goldstone bosons are pure gauge. What do I mean by that? So Goldstone bosons are pure gauge. What I mean by that is they're fake. They're only there because of gauge, without gauge invariance, right? They're only there because of a choice of symmetry. They're a pure gauge object. They can be gauged away, quote unquote, right? We can gauge them away, which is what we've done. Okay. Okay. The last thing I'll leave you with, which I'd like you to read, is on. So here's the last thing we'll do today. So does anyone have any questions about any of that before we do the last little thing? Okay. I mean, that's pretty fascinating, right? That's pretty amazing. Okay. So let's do one more quick thing. So like I said, quantum field theory is very, very constricting, right? I keep saying that. I'm going to show you an example of that, okay? So I'm going to show you that you cannot have symmetry breaking if your universe is 2D or less, okay? You can't have symmetry breaking in a universe that is less than 2 dimensions. Okay, let's do a quick proof of this. So let's say I have some 2-point correlation function at the origin, okay, or some like starting point. That amounts to calculating psi hat of 0 squared, right? That's what I mean by my correlation function, some vacuum expectation value. And of course, I'm going to get back some Green's function, right? So I'm just starting with this basic object. Now I can write this out as a functional integral or a path integral to calculate this. So I can write this out as some d psi hat naught squared e to the minus s phi. Right, so this is our basic path integral or functional integral. And if I solve this guy, I get some vacuum expectation value, right? And this is in d dimensions, right? d phi, some d-dimensional thing, okay? And what do I get when I solve this? This is just a vacuum expectation value. I get the standard Green's function. What is the standard Green's function in quantum field theory? It's just the propagator, right? Right? So I just get the propagator back. So you do this calculation. We've done this calculation. And you get some propagator. Since this is a fermion, it looks like psi hat of x, psi hat dagger of y. Right? And what does the propagator look like? Well, it looks like our standard guy. I'm going to put it in d dimensions, so ddp over 2 pi to the 4th. E to the minus I p dot x minus y squared plus m squared. Right? Our standard propagator, right? That's just, this was like the kind of stuff we did the first few weeks of Q of T, right? Taking these correlators and getting propagators. And their Green's functions, right? Just by the natural construction. Okay. So so I told you that you can't have symmetry breaking unless you have dimensions over 2. So let's see how that works. There's a very easy way to see this. So you have this, e to the minus I p dot x minus y, p squared, m squared. Okay, so in symmetry breaking, you have massless Goldstone bosons, right? So this is just 0, right? Right? So now let's just rewrite the propagator. So now my propagator becomes d dp over 2 pi to the 4th, e to the minus I p dot x minus y over p squared. Oh, and actually even this exponential goes away because I have no mass describing this guy. So there's no exponential. And I'm left with a very simple propagator, 1 over p squared. Yeah. Cool. So in symmetry breaking, this is the kind of propagator we get for the massless boson, Goldstone boson. Okay. This has a very simple analytic structure. What do I mean by analytic structure? Meaning it's complex structure. So it's analytic structure. It just has one simple pole, right? At p squared. That's the only simple pole. So it just has a simple pole at p equals 0, right? That's the only. Do you guys know what I mean by that from complex analysis speak? Okay, good. We have done these kinds of integrals, right? What do? We put our plus I epsilon prescription, right? And we shift the pole, right? That's like, and we pick a contour, and it's like a basic thing we do all the time in Q of T, right? Shift the pole, shift the contour, close the contour, go around. It's like all of these things. Which actually, if you think about it, guys, I'll give you 2 complex analysis tips. 1, where are all the poles going to be most of the time? At the origin, right? That's where all the poles are. So that's a simple way to think about it. You just have poles at the origin. And second, when we talk about residues, what's a residue? It's everything except the pole. So what's the residue of the pole here? It's just 1 over 1. The residue is just 1, right? Because my pole's in p squared. And these are just 2 simple things. Okay, good. Okay. And now, turns out, if d is less than or equal to 2, this integral diverges. You cannot fix it with I epsilon. Okay, so you can look up why. So this is called Coleman-Wigner theorem. This is the Coleman-Wigner theorem. And it's a very simple process. And it's a very nice example to show you how constricting Q of T is. You cannot have symmetry breaking. If you want symmetry breaking, if symmetry breaking is a part of the universe, that's what happens. If you have this Higgs boson out there, which comes from symmetry breaking, and it's a thing, and you have to live in a universe that's greater than 2 dimensions, which we do. That's kind of cool, right? You get a divergent thing. You cannot correct it with complex analysis. Okay, good. So we did a lot today. So let's recap in the last 5 minutes. Nature is very, very fascinating and strange. I think anyone who does any physics for long enough starts to understand this, that nature is very strange. And I think this is one aspect of this. What I like to say is the fact that So if you think about this from a theorist point of view, right? I think the fact that these mathematical constraints or this imposing our symmetries on our equations, the fact that it gives strong physical results is very good, right? It's very encouraging that perhaps the right way to think about mathematics and physics or physical theories is with this sort of desire for symmetry. So that's the right way to think about this. And it's strange. I'm not really sure, because when you first read about gauge invariance, which you did in Lancaster-Blundell, so you read that electrodynamics is the simplest gauge theory. And you read that, okay, you work in Lorentz gauge, and tomorrow, for example, with gravitational waves, we're going to be relying heavily on gauge, on picking a gauge. That's going to be a big part. So at first glance, it seems like, okay, this is like a nice physical way to do business. But you very quickly realize that this gives some very deep, profound physical insight, which is very good. Okay, great. So next week we will do spinor helicity and CFT, and I'm going to start taking you to the frontier. And actually, you're going to be surprised. The calculations aren't that bad, actually. Actually, I like to tell people you do most of your character building calculations in QFT. And after that, actually, things get pretty simple. It's more about extracting deep insight, right? In the simplest way. And you're going to see that with this whole scattering amplitude program. It's not that confusing mathematically. Well, it is, but not that bad. And if you have questions tomorrow morning about this, stop in a little bit earlier before a little group meeting. And I'll see you guys tomorrow. And if you need more time on the GR questions, no problem. Take an extra week, okay? Because I know you're sick. You're traveling, right, Olha? I'll stop recording. You're traveling, right?
Yeah.